Hello everybody, this is Dr. Ritin Kumar, Assistant Professor, AJ Institute of Engineering and Technology, Mangaluru. Dear students, today I am going to discuss the topic, that's the last topic of Maxwell's equations. Okay, so in this topic now we can see the first topic called as equation of continuity. So what is this equation of continuity? So now let us consider a closed surface, a volume of charge density rho. So we have to consider a closed surface having a volume charge density rho. If there is any charge flowing from this surface, then charge through that small area is given by J dot ds. What is J? J is known as here the current density. J is known as here the current density, and ds is the small area. So this let us consider. So we have to consider a closed surface, okay, having the volume charge density rho. If there is any charge, that means see we are having a small closed surface like this, is closed surface like this having large number of charges, okay. So if the charges flow from this surface a small area, so if the charges are flowing from this surface, now let us take that flow of charges is J dot ds. Here ds represents the small area of the consideration, and what is J? So here we are telling that charges are moving from the small area. So movement of the charges always constitute the electric current. So there it's a current through unit area. That's why we are considering it as a J vector. So charge flowing through the small area is J dot ds. Total amount of charge flowing outward. So now the total amount of charges which is coming from this small area is given by closed integral of J dot ds. Okay, so total amount of charge flowing. So J dot ds, if you consider like this one small volume, and if this is a small area, then charges coming through the small area we have written as J dot ds. When you consider the total charges coming out from the entire volume, from this total volume, then it is given by closed integral of J dot ds. Now let us consider a small volume inside the surface. The charge in the volume is rho dot dv. So in this one, so let us consider a small volume. So the charge in that volume is given by rho dot dv. Okay. So charge in the entire volume. So in the small volume it is rho dot dv. So charge in the entire volume is given by closed integral of rho dot dv. Okay. So next, see what happens here. So as the charge flow outward, the net charge present inside the volume decreases with the time. So here what happens, so more and more charges are going to come out from this surface. So like this it is almost like see here it is. So if this is the charged area, if more charges are going to come out, what happens inside this one? What happens? So here the net charges in this volume decreases. So I have written, as the charge flow outward, the net charge present inside the volume decreases with the time. As the time increases, the number of charges goes on decreasing. So further, therefore, the amount of charging flowing outward is equal to decrease in the charge inside the volume, as that is what we saw in the last one. So as more and more charges come out of the surface, the number of charges inside the volume decreases. That is a diminishing. So next one, so that it can be written as, so here the same thing we are writing it as, so here J dot ds in a closed volume J dot ds. So here it indicates the charges flowing from the closed surface. So as the charges move from the closed surface, what happens? The number of charges in the closed volume decreases. That is just like you take 1 liter of water and you just pour 1 liter of water to a bucket. So as you go on pouring the water to the bucket, so 1 liter reduces to 900 ml, so it reduces to 800 ml, it reduces to 700 ml. As it goes on decreasing, the volume of the water goes on decreasing as the water moves out of a liter. Okay. So in the same way here, so you can see as the charge j dot ds increases or it goes out, charges goes out, the net charges inside the volume decreases, though that is given by the negative sign. The negative sign here, it is symbolizing that the decrease in the charges. So we know from the divergence theorem, that is the divergence theorem always relates between the surface integral and the volume integral. So closed integral j dot ds, closed integral j dot ds. So this closed integral j dot ds can be converted into a volume integral, closed volume j dot del dot j into dv in the closed volume. Okay. So next, hence, so we know j dot ds is nothing but minus dou rho dou by dou t closed volume of rho dot dv, and this j dot ds is nothing but we have know that according to divergence theorem, this j dot ds can be written as in terms of volume. So this let us substitute in the place of this one. Okay. So just eliminate that one and substitute. Hence we get the equation as closed volume j dot del dot j dv is equal to minus dou by dou t closed volume rho dot dv. Why we have written is because both should be in the volume, the equation should be in the volume further for the continuation. So here next we can write that, so just take this dou by dou t inside the integral, so it can be written as, so closed wall integral j del dot j into dv is equal to minus, you take this dou by dou t inside the integral, so it is closed integral volume v dou by dou t rho dot dv. So further what happens here is, so in this one, so it is a closed volume integral and integral gets cancelled out, and here dv and dv gets cancelled out. So it can be written as del dot j is equal to minus dou rho by dou t. Del dot j is equal to minus rho by dou t. Okay. So this is actually called as a equation of a continuity. Okay. So what is this continuity equation? So this equation of continuity, whatever we have seen in the last slide, this equation of continuity, what we have seen in the last slide is, so this one equation of continuity, that is del dot j into rho minus dou rho by dou t. So this equation of continuity finds application in many fields. For example, in the fluid mechanics also, we can write the same equation as like this. So it can be written as, so we can write in this way also, something like m is equal to you can write closed volume dv by into p. So in the case of fluid mechanics, to calculate the conserved field in the total mass of the fluid, even in the heat conduction also, this can be written as dou t by, it is dou t, that is equal to variation, that is k into delta t. So that gives you actually the heat of conduction, but is thermal energy, which that is the equation for thermal energy. So it gives you the idea of heat flux, so amount of heat flux going out of the surface. So even you can see the diffusion of the gases when you allow the gas, for example inside a balloon the gas is there, and just to make a small hole and the gas diffuses from inside the balloon to outside. So as the gas comes out, net volume of the gas decreases. So that can also be calculated by using such equations, equation of continuity, which is help in the heat conduction equation. So we can write it as dou n by dou t. So like this also we can write dou n by dou t is equal to d, we can write even del dot n. So in this way equation of continuity is having a lot of applications, but in your syllabus they concentrated only on the Maxwell equation. So the amount of charges flowing out from the closed surface, as a result that net charges inside the volume decreases. So actually that is the idea. So that is minus dou rho by dou t. So this is the equation of continuity. Okay. Now let us go for the next concept, that is Maxwell Ampere law. So what is this Maxwell Ampere law? Maxwell Ampere law, see, let us consider the Ampere's law. See, Ampere's law tells you that del cross H is equal to J. So curl of a magnetic field represents the current density. So now what, what we do, let us make some simple steps. So now let us take del, apply divergence on both sides. So when you apply, so here we are applying divergence, so del cross H vector is equal to del dot J. Okay, since the curl of the since the divergence of curl is 0, see, we know divergence, what is this J is a vector, so divergence of vector is always equal to 0. So divergence of J is equal to 0. So as a result, further, so the equation can be written as, so you can write the equation as actually, so del cross H is equal to 0. But anyways, this means the divergence of the current is 0, that there is no net charges accumulation or charge loss of charges. There are no sources or sink of the current. This is true in case of steady current, which the continuous throughout the circuit. So in case of continuous steady current, this is happens to be true. The divergence of the current is 0. But it is not in case of a non-steady current or current which varies with the time. Anyways, so next one. So however, the in the circuit containing the capacitor, so when you consider the capacitor, so here in case of this one capacitor, during the during the discharging, the current starts at the positive charge and charge diminishes as the current flows through the negative charges when it is accumulated. Hence we can look upon the condenser plate as source and sinks of the current. So you can even illustrate that the displacement current arises in the connection of capacitor with no medium between the plates. The capacitor equal and opposite charges on the left plate and charging the capacitor and increasing the electric field. But we can see the no actual charges is transmitted through the vacuum or something like that. So what we are going to what I am going to tell you that, hence due to the positive charges, the charge diminishes as the current flow to the negative charge plate which is accumulated. Hence we look upon the condenser as a sink. That means positive and negative charges just like coincides. So hence Maxwell conclude that del cross H is equal to J is incomplete. So besides this, there should be a some added term. So what he tells that del dot J, we know from the equation of continuity, so del dot J is equal to dou rho by dou t. As we saw, more and more charges go out of the surface, the net volume decreases. As the charges go out of the surface, it contributes for the current density. So we write here del dot J is equal to minus dou rho by dou t. So further, uh, so del dot J is equal to, but what is that one del dot J? So it is equal to minus dou by dou t del dot D. So we know that rho is nothing but according to the Maxwell first equation. So what does the Maxwell first equation tells you? Maxwell first equation tells you that, see, it gives you so del dot D, del dot D is equal to rho. So it tells you that del dot D is equal to rho. So that is del dot divergence of electric displacement is equal to density with respect to A. So here, so this rho is replaced by this equation. So we can write this equation here, del dot D is equal to rho V, or simply rho, or it is minus del. You take this del outside, so this dou by dou t goes inside here. So it is minus del into dou d by dou t. Okay, this I have written here. So next, that is del dot J is equal to minus dou into dou d by dou t. So further you take this from this equation, so you take this one to this side, so it is del dot j plus del dot dou d by dou t is equal to 0. So or you just, since there are two del here, del and del here, so you take the del outside. So as you take the del outside, so del comes out, so remaining will be the j vector plus it is dou d divided by dou t, dou d by dou t, or that is equal to 0. That reduces to 0. Okay. So next, thus del dot, see here what happens in this expression is, so what happens here is, see, either in this one we can write like this, so just like this equation, x dot y is equal to 0, so both can't be 0. How to write? So x equal to 0, or we can write y equal to 0, or I can write or y equal to 0, or okay. So here del equal to 0, that is or j plus dou d by equal to 0, but del dot j is not 0, it is not 0, but divergence of j plus dou d is always equal to 0, so it is always equal to 0. Hence Maxwell made an assumption that j in Ampere's law must be replaced by, so he tells that j current density is replaced by some other expression j plus dou d by dou t. So further, so for the time varying field, in the sense, as you know, when it is connected to the AC circuit, so positive charges gets accumulated in the one side of the plate and negative charges gets accumulated in the other side of the plate. Again, when the for the negative half cycle, again the negative charges will be accumulated in the positive side of the plate, and positive charges will be accumulated in the negative side of the plate of a capacitor. So like this, for the time varying field, so it can be del dot h is equal to j plus dou d by dou t. Hence the term is called as displacement current. So it is called as displacement current. So in the electromagnetism, displacement current or displacement current density is a quantity. So what we have written here, so it is a quantity dou d by dou t appears to Maxwell equation, that is in terms that defines as term of rate of change of d, the electric displacement field. Generally the displacement current density has the same unit as electric current density. It is having the same unit, so almost concept is same, and it's a source of magnetic field just as an actual current is. However, it is not an electric current of moving charges, but it is time varying field. In physics material, there is also a contribution from the slight motion of the charges bounded by the atom also, which is also because of dielectric polarization. So the Maxwell was the scientist who added this displacement current to the current term in case of Ampere's circuit law, or simply called as Ampere's law. And the amended version we simply call it as Ampere circuit law, or it is a dynamic theory of electromagnetic field in terms of Maxwell equation. The derivation is now generally accepted in a historical landmark in the physics by virtue of uniting electricity, magnetism, optics, and onto single unified theory also. Okay, so the displacement current is now seen in crucial addition that completed Maxwell equation and is necessary to explain many phenomena, so most particularly the existence of electromagnetic waves, that we can see in the coming videos. So displacement current density is actually, in a one word to define it as, displacement current density is the current in the insulated region due to the changing electric flux. It is very clear from the above expression that the rate of change of electric displacement produces magnetic field just as the conduction current does. So last concept here, Maxwell equation in word form. We have seen all the Maxwell equations in the last class videos and all. So the first one, the total electric flux density through a closed surface enclosing a volume V is equal to the total charges within the volume. So the equation we have written, del dot D is equal to rho, and rate of change of electric displacement. so del dot D is equal to rho. Second one, total magnetic field flux emerging through a closed surface is equal to 0. So total electric flux through a closed surface is equal to 0. So divergence always symbolizes or always applicable for open loop quantity. For a closed loop quantity, divergence is equal to 0. Okay. The third equation of Maxwell, the magnetomotive force around a closed path is equal to the conduction current. Okay, so magnetomotive force around the closed path is equal to the conduction current. Conduction current, it symbolizes both. One is current density plus rate of change of electric displacement through the surface bounded by the path. Okay, so we have seen that correction. Now earlier we have seen only del cross H is equal to J, but Maxwell made a correction, this one. So it is del cross H is equal to J plus dou D by dou T. So it is called as modified Ampere's law. Next one, the electromotive force around a closed path is equal to the rate of change of magnetic flux through the surface bounded by the path. So it is given by del cross E. So del cross E is equal to minus dou B by dou T. So it is the rate of change of electromotive force around a closed path is equal to rate of change of magnetic flux through the surface bounded by the path. So it is actually called as Faraday's law that we have seen. Okay, so next last one to discuss is the integral form of Maxwell equation. So what is this integral form of Maxwell equation? So integral form of Maxwell equation tells you that first one, d dot ds, closed surface integral of d dot ds is equal to volume integral rho dot dv. That is first one in a closed surface. So closed surface integral b dot ds is equal to 0. That is second one. Closed line integral h dot dl is equal to surface integral j plus rho d by dou t. That we have seen. H that is we have del cross H is equal to this much, same thing. Now we are writing in terms of integral, it is line integral and this is surface integral. So we write it as line integral H dot dl, line vector, both are vector, is equal to the closed surface integral j plus dou d by dou t. Okay, so next one, line integral E dot dl is equal to the minus surface integral dB by dt into ds. So you know Maxwell displacement, the equations are a phenomenal equation, so which is actually responsible for different kinds of phenomenon like your motor, dynamo, etc. Whatever generation of a magnetic conversion of magnetic field to the current, etc. Everything stands in this four equations. That's why it is told that these are the God-given equation which changed the path of human life. Okay. Thank you. So I can complete this one as God said, del dot B is equal to 0, del dot D is equal to rho V, del cross E is equal to minus dou B by dou T, del cross H is equal to H plus dou D by dou T, and then there was a light, and because of these four equations you can convert magnetic field to the current or current to the magnetic field, etc. There throws the line. Okay. Thank you.